Since heap is a heterogeneous computing platform, we have the flexibility to either use the CPU or the GPU for computing or even use them at the same time. To control both devices, heap needs asynchronous computing, which is supported by the heap stream feature. In this video, we will discuss about heap streams, providing a comprehensive understanding of what they are and how they work in a heap program. So far, we have been transferring data and performing computation serially in the previous examples. Let's review the serial vector addition we did previously. In that implementation, we transferred arrays A and B from the CPU to the GPU, performed computation using the vector addition kernel, generated the array C, and then transferred the array back to the CPU. During the transfer of A from the CPU to the GPU, we only utilized one direction of the PCIe interconnect, causing the GPU to remain idle as the GPU does not execute kernel during this time. Similarly, during computation, the PCIe bus was idle in both directions as the GPU was busy executing the kernel. Then during the transfer of the array C from GPU to the CPU, only one direction was utilized, leaving the GPU idle once again. As a result, the bandwidth of the PCIe interconnect was underutilized, as was the GPU. To solve this problem, we can use heap streams to overlap data transfer and computation and efficiently utilize both the PCIe bandwidth and the GPU. A heap stream can hold a sequence of tasks that can be executed in order on the GPU. Using streams, a programmer can define multiple tasks for the GPUs at once without waiting for the running task to complete execution. Moreover, tasks from different streams can be executed asynchronously. So with multiple streams, programmers can schedule and execute tasks concurrently on the GPUs. The task can be kernel launches, memory transfers, or any other operations that can be executed on a GPU. Especially using heap streams can execute multiple kernel concurrently to improve performance. When a single stream is used, heap streams can be used to manage dependencies between tasks, ensuring that they are executed in the correct order. In heap, all tasks or operations that are performed on a device such as GPU are associated with a particular stream. This stream acts as a queue for these operations, ensuring that they are executed in the order in which they are added to the stream. Essentially, the stream helps to coordinate and organize the various tasks and operations running on the device, helping to ensure that they are executed efficiently and effectively. And scheduling work from the host into a stream is considered non-blocking because it does not wait for the work to finish before continuing execution. Instead, the work is added to the stream and the host continues executing the next steps in the code without waiting for the work to finish. This enables the host and the device to work in parallel and improve performance by overlapping computation and communication. This mode of parallel computing is also known as asynchronous computing. Let's go deeper into the topic of asynchronous computing in heap. Asynchronous computing with heap refers to a mode of parallel computing where multiple computational tasks can run concurrently without waiting for the completion of any single task. Thus, streams allow GPU to overlap the execution of multiple kernels. By launching multiple kernels on different streams, the GPU utilization can be maximized. Without using streams, the GPU may be underutilized as it waits for the data transfer or kernel execution to complete. When a kernel completes execution, the host can check the status of the stream and take appropriate action such as copying data from the GPU back to the host or launching another kernel. Heap mem copy async is a function in heap that allows for asynchronous memory copy operations between host and device memory. When we use the heap mem copy async function, the memory copy operation is enqueued in a specified stream rather than being performed immediately. In this function, we must mention the source and destination memory addresses, the size of the data to be copied, and the direction of the copy, just like the heap mem copy, except that we also need to mention the stream in which the operation should be enqueued. Now we will explore how to incorporate heap streams into our code, including the relevant functions and techniques. Now let's see how we can create and allocate a stream in the GPU. heap stream underscore t is a data type in heap that represents a stream in the GPU. It can be declared as heap stream underscore t stream to allocate a stream in the GPU. The function heap stream create is used to create an asynchronous stream in the GPU. It takes a pointer to a heap stream underscore t as an argument, which is used to return the handle to the newly created stream. The function heap stream destroy is used to deallocate the stream from the GPU. It takes a pointer to a heap stream underscore t as an argument, which represents the stream to be destroyed. But before destroying this function, waits for all the work in the stream to complete. The function heap stream create with flags is used to create an asynchronous stream in the GPU with specific flags. It takes a pointer to a heap stream underscore t, which is used to return the handle to the newly created stream, and an unsigned int value, which represents the flags to be used while creating the stream. Some examples of flags are heap stream default and heap stream non-blocking. The default stream is a special stream that is created automatically when the heap context is initialized, and it is used to queue heap operations that are not explicitly assigned to a user-defined stream. And using heap stream non-blocking flag can improve the performance of heap programs by allowing asynchronous execution of operations which can overlap CPU and GPU computations and reduce overall execution time. However, when a stream is not specified in a heap program, it uses a default stream for kernel execution. So default stream is used when only one kernel is invoked. And when we execute asynchronous heap commands without specifying a stream, the runtime uses the default stream. Now let's take a look at an example where we will be using two separate kernels and two streams for computing the square and cube of an input array. To get started, we need to include the necessary header file. In this code, we will be using n to use the constant, as the value of n is an integer argument that represents the number of elements in the array we are going to consider later. After including the necessary header files and macros, we proceed with writing GPU code. In this example, we will be using two GPU kernels to perform two different computations in parallel. The first kernel is responsible for squaring the components of the array. This kernel is similar to a typical kernel and includes thread indexing and a computation to calculate the square of each component in the array. The function square kernel takes two input arguments, input and output. Both of these are pointers to arrays of floating point numbers. The first line of the function calculates a thread ID. The next line of the function performs the actual computation, squaring the input value at the current thread ID and storing the result in the output array at the same index. Similar to the square kernel function, the cube kernel function also takes two input arguments, input and output. The cube kernel function computes the thread ID and performs the computation by cubing the input value at the current thread ID. The result value is then stored in the output array at the same index as the input value. In the main function, the code initializes 6 pointers of type float. The h_input pointer is used for input data on the host. h_out_sq is used for the output data from the square kernel on the host. h_output_cube is used for the output data from the cube kernel on the host. Similarly, d_input, d_output_sq, and d_output_cube are pointers to dynamically allocated memory on the GPU. We allocate memory for these pointers on the host using the malloc function, with the size of each memory allocation determined by the size of float multiplied by n, which we have defined earlier as a macros. Next, we initialize random values in the input array of the host. Then we use heap malloc function to allocate memory on the GPU, similar to the allocation on host memory. In this case, we allocate memory for all three pointers on the device d_input, d_output_sq, d_output_cube. This block of code initializes two heap streams using the heap stream create function provided by the heap API. Two streams are used here to overlap computation and data transfers, which can improve the overall performance of the program. The code first declares two stream objects called stream1 and stream2 of type heapstream_t. Then the heapStreamCreate function is called twice, once for each stream object. This function creates a new stream and initializes it with default properties. The function takes a pointer to a heapstream_t object as an argument, which is used to store the newly created stream. The two stream objects, stream1 and stream2, are initialized and can be used to execute heap commands asynchronously on the GPU. We are utilizing the heap memcopy async function for asynchronous memory transfer, as it can improve performance by allowing data transfer and computation to overlap. In contrast, the heap memcopy function is used for asynchronous memory transfers, where the CPU waits for the data transfer to complete before continuing execution. In short, heap memcopy async should be used when multiple streams or kernels can execute concurrently and we want to overlap memory transfer with computation. On the other hand, if we have a single stream or kernel, we don't need to overlap memory transfers with computation and can use heap memcopy instead. After setting up the device and host memory, we determine the block size and grid size for launching a kernel function called square kernel. Note that since we use the asynchronous version of the memory copy API, we can calculate the block size and grid size and launch the kernel without waiting for the memory copy to complete. As long as we add the kernel to the same stream, the kernel will be guaranteed to execute after the memory copy is completed. Here, the block size is set to 256 and the grid size determines the number of blocks that will be launched. Then we launch the kernel function with 4 parameters. The first two parameters are the block size and the grid size, like in previous examples. The third parameter is the shared memory usage for this kernel, which is set to 0, and the fourth parameter is the stream on which to execute this kernel, which is stream 1 in this case. By specifying stream 1, we are indicating that the kernel launch will be asynchronous and will not wait for previous operations to complete before executing. The kernel takes two arguments d_input and d_output_sq, which are the pointers to the input data stored on the device and a pointer to the output data buffer where the result of the kernel operation will be stored on the device. We use the heap memcopy async function to transfer the data calculated on the GPU back to the host. Still, as the kernel is launched asynchronously, this memory copy API is queued before the kernel completes execution. Similar to the previous data transfer, we specify the same stream, stream1, on which to execute this asynchronous transfer. Since the kernel and the device to host memory copy are scheduled on one stream, the memory copy will start after the kernel completes execution and hence we can have the updated data. We will now execute the second kernel function, which is kubekernel. Like before, we will also use a stream to perform this operation. However, this time we will use stream2 instead of stream1. Similar to previous kernel execution, we will also pass two parameters to the kubekernel function, d_input, which is the pointer to the input data stored on the device, and d_output_cube, which is a pointer to the output data buffer where the result of the cube computation will be stored on the device. We are now transferring the results of the second kernel from the device to the host, but this time we are using stream2. By using a separate stream for this transfer, the data transfer and kernel execution for the second kernel can overlap with the data transfer and kernel execution of the first kernel on the GPU. This technique allows for better performance and can help reduce the overall execution time of the program. After launching the kernels on different streams, we need to ensure that all the commands issued on those streams are completed before proceeding further in the CPU code. To accomplish this, we use the function heapStreamSynchronize, which waits until all the previously issued commands in the specified streams have been completed before allowing the CPU to continue execution. This is important because it ensures that any subsequent instructions that depend on the results of the kernel will have access to the correct data. By calling heap stream synchronize on both stream 1 and stream 2, we ensure that both the square and cube kernels have completed execution and that their respective results are available for further use in the CPU code. Then we are deallocating the memory that we have allocated for both CPU and GPU. Finally, we are returning 0 to indicate the function has executed successfully without any errors. So far in this video, we examined how streams can be leveraged to optimize GPU utilization by overlapping data transfer and computation. We explored the benefits of running multiple kernels concurrently to further enhance performance and introduced the concept of asynchronous computing in heap. In addition, we presented various techniques for implementing application streams in a program, including the use of two separate kernels with streams. In the next video, we will discuss two important types of memory allocation in heap.